I'm going to be doing homework 4, part B. So in part A, we had the 3 tanks in series. And to solve this, what we usually did was we did derivatives of these. We did our derivative functions. Instead, we did Laplace transforms, and we changed time-dependent equations of this, and we changed it to deviation functions, and then we got our transform functions from this. So today, and from those, we can use the Bode frequency. We can use Bode frequency to solve for this stuff. So the first thing that we want to do today is we are going to have is our tau. So like we already derived with our transfer function that we had our k, our tau, and our s, and our kc as well. So our tau, let's start it off as 1. And then our k, which is our process gain, we're going to have that as 2. Yeah, 2. And then we have our kc, which is our controller gain. That one is going to be 0.5. And then we have an s, but we're not going to do an s, and I can show you why after this. So g is going to be our transfer function. So let's create our transfer function. So we have kc times k divided by tau times s plus 1 to the third power. So we have this, and so it says that Python has our s here and that it's not defined. It doesn't give us an error message, and this is because when we type in RG here, it gives us this. Let's change this to 1 actually. There you go. So we have tau, k, kc, and then our s. S is our time step. So this is going to allow us to have s as kind of in a function. So g is going to be kind of our function, and then we can substitute g in later for this, right? So we are going to be doing a Bode frequency. So when we had this in our imports, that gives us our Bode frequency. So we do is Bode. So we're doing the Bode frequency of our transfer function. So if we look at this, we see that we're getting multiple different arrays, right? So what they're giving us is the first one is going to be our figure. Our next one is going to be, look down here, should say well, our next one is going to be our magnitude. And then the next one is going to be our phase angle. So we can have it like that. And we have that. So now let's see what the figure has given us. Figure show. So we're given 2 graphs. So the bottom graph here is going to be, we have our frequency down here, and this is going to be our phase angle. So our phase angle from 0 to negative 180 to a very large number, a negative number. So we are going from this phase angle, and these down here are going to be our frequency in radians per time. It's going to be, so this is going from 0 to 180, and this is going to be our phase angle. Over here is going to be our frequency, which is in radians per time unit, and that time unit is whatever tau is per unit, whatever tau's unit is. in time. So what we need to figure out is what is our crossover frequency. Our crossover frequency is what is our phase angle at 180. So what is our frequency at 180? And it tells us that it is about 1.8. So if we go up here and we look for 1.8, 1.8 is going to be 0.554, right? So with that is under, so up top, so this blue here is going to be our amplitude ratio. Our amplitude ratio, we want to know what our amplitude ratio is at our crossover function. So our crossover function is less than 1, right? So it is 1.8. Okay, so I did fix something. I changed tau from 1 to 2, and I think this gives us a better result from what I practiced. So our negative 180 angle for our phase angle gives us our negative 180 for our phase angle, which gives us our crossover frequency, is going to be 0.87. So that, if we go up here to 0.87, this is our amplitude ratio. And we want to find what our amplitude ratio is when our crossover function is 0.87. So here. So it's going to be 0.618, right? This is under 1. Our amplitude ratio needs to be from 1 to 0. You can get smaller or bigger, but just 1 to 0, and you have stability. So from that, knowing that, we are going to do our GCL. Now, our GCL is going to be our transfer function of the closed loop. So when I had made our, like the block diagram, we saw that we had our height set point go in, and we had first, we wanted to see that I had an error, and then from that error, we changed the proportional controller of KC, and that went into our transfer function of the processes, right? Our GP, and that changed our height of the tank of 3. And then we had a loop to go back to check that height of 3 to our comparator to our height set point. And then from that, we got the error, right? So with our closed loop, we are going to do everything that is going forward. So our forward of that block diagram is the error, is pretty much our G. And then we're doing 1 plus everything that's in that closed loop. Since we didn't draw anything on the bottom of that closed loop that wasn't going forward, we're just going to signify it as 1. So we can do in this GCL, in our transfer function in the closed loop, we can do is G divided by 1 plus G. Now, we can change this down here to see what it looks like of GCL. And see, now we have a much more difficult function where we have S in there. So, after this, we are going to want to use our simulate, right? So we're going to use our function simulate, and we're going to use the closed loop function that we have. We're going to use lambda, and we're going to do this as a time step of 1. So it's doing a 1 time step. Then we have our n, which is how many times do we want to split this up? Let's say 1,000. And then how much do we want to move for every time step? which is going to be 0.1. Then this is going to be, so let's just look at it right now. So you're going to get two arrays with this, right? So your two arrays are going to give you your t-plot and your height plot as well. So now we have those. Now we have those two. We can make our graph. So fig is make underscore subplots. And then we do fig dot add underscore scatter. X is equal to t. Y is equal to h plot. Mode is equal to lines. So let's look at this. So we have a function where we bumped up and then we're at a steady state as time progresses, right? So what if we changed our proportional controller gain to 10? So let's do that. So we can see that we're having instability, right? We're having a lot of oscillations, and that is causing us to go up and down by huge numbers when we were doing 0.3. Now let's look over at our figures for our mode frequency. So our crossover function is still at 0.87. So let's look for 0.87 up here. 0.87, it looks like our amplitude ratio is 1.23. Now, with our amplitude ratio being over 1, we're going to have instability. That is why we have instability, is because our amplitude ratio is over 1. So from this, we want to see what is the biggest controller gain we can have with our function. And so we can have it as, let's divide it by what our amplitude ratio is. So it's 1.23. Now we can see that we're having a lot of oscillations to this, right? But we're not really, we're having a little increase or a decrease on that, but it's not crazy. We're not going to 30, we're not going to minus 30, we're staying above. We're usually staying above. We have a little bit of negative down here, and that is probably due to round off error, right? We didn't get it correct. But this is showing that we're having oscillations and we're still kind of like not having variability. We're still having a stable function here. Now if we go up and we try to fix that round off error and go down here, let's see. Now we're having more stable oscillations. Very little is going to the negatives, but let's look up here. So our crossover function doesn't really change. It's 1.87, right? So let's go up here with 1.87. Okay, so you can see that it's almost at 1, just a little over 1, right? So another thing that we can do is our crossover with our controller gain, we can half that, and we can have a half of amplitude ratio. So you just divide it by 2. And so this is going to give us some oscillations, but then we're going to have stability as time goes on with our heights. And then if we look over here for our crossover frequency, it's going to be half of what it was, the amplitude ratio. So that is the end of homework part B.